Okay, so we are in Introduction to Statistical Learning, Chapter 6 here, and we're on the conceptual questions, question 4. We'll get into question 4 here in a second, but I want to compare it with question 3. And in question 3, we were looking at the lasso, and we're asked some questions about the lasso, okay? And now we're asked about ridge regression, okay? And you can tell the difference because ridge regression has a penalty term that is penalizing by the sum of by the sum of the square of the beta coefficients, whereas the lasso is penalizing according to the absolute value of the coefficients. So now in question 3, again under the lasso, we were given this formulation right here, okay? That we would minimize the residual sum of squares subject to this constraint, okay? And that constraint is defining basically the lasso penalty. And I said that I tend to like to think about this in this form here instead, where this form, I'm adding the penalty, and the penalty is lambda plus, the penalty here, and that this form was, it was roughly equivalent to something like this, 1 over s, right? So the constraint here was saying subject to, this penalty being less than some value s, okay? And so lambda is I was making the case that it's, roughly equal to 1 over s. And I don't even like saying roughly equal because it's a little bit misleading, but it's acting like 1 over s, okay? And so then we went through and we talked about as s varies from 0 to infinity or whatever, what happens to the training residual sum of squares, the test RSS, the variance, bias, and irreducible error. Okay. Now we're going to do the same thing for ridge regression instead of lasso, but instead of talking about s, we are now talking about lambda. Okay. Well, this should be fairly easy because lasso and ridge regression are very similar, and lambda and s are roughly working as inverses. Okay, so at the end of the last video, I reproduced, or I kind of doctored up this image that is in the book itself. And it usually goes lambda, where lambda starts small here on the left and goes to the right. And because lambda is acting like 1 over s, we could also read this as going from right to left, where s gets small to big here. Okay, something like that. All right. So again, here in 4, we're looking at ridge regression, and now we're asked what happens. We are given the ridge regression in this formulation, okay, and we're asked what happens as lambda goes up, okay, from 0 to whatever. Okay, and we're asked again about the training residual sum of squares, the test, the variance, bias, irreducible error. Okay. And we're meant to say, does each component, does it increase initially, does it have a U-shaped curve, up or down? Does it steadily increase, decrease, or remain constant? Okay. Now, so for this, we really can use this image right here that's present in the book, and we can read from left to right, just as it's presented in the book. Okay. So we'll go through all of these. So let's talk about the training residual sum of squares. This is actually the only one that cannot be read off of this image right here. So let's talk about it. Okay, so let's think about what happens as lambda goes from 0 and then increases. Okay, so as lambda goes from here and then gets bigger and bigger and bigger. All right, what's going to happen to the training residual sum of squares? Okay, well, when lambda equals 0, okay, when lambda equals 0, that means that this term right here is 0, and this term right here is the penalty. So when lambda equals 0, the entire expression is minimally constrained. Okay, it is just simply the normal least squares criterion. Okay, so as lambda gets bigger, then we are imposing a larger and larger penalty. Okay, in other words, we're making it more and more constrained. All right. So what is going to fit the training data the best? Well, it's going to be the least constrained model is going to fit the training data the best. So as lambda gets bigger, then the error should steadily increase, right? Because we're fitting it worse and worse and worse as lambda gets bigger. Okay, so that's for training residual sum of squares. Okay, so how about now for the testing residual sum of squares? All right, if we go back up here, once again, okay, now we're talking about testing residual sum of squares. Okay, and again, as lambda gets bigger, the model gets more and more constrained. As lambda approaches 0, it becomes not necessarily unconstrained, but constrained only based on the normal least squares criterion. Okay, so so assuming that the best model is not maximally constrained nor minimally constrained, then when lambda equals 0, we won't have an optimal fit. Okay, so there's going to be some residual sum of squares that could be improved on. So that means as we constrain the model more and more and more, okay, our model will do better. Okay, the residual sum of squares will get smaller to a point when the model is over-constrained. In other words, lambda gets so big that the constraint is now, more penalty than it's worth, or making the model fit worse than we would want it to. Okay, so we should see kind of a two-phase, fitting thing. So it should initially decrease and then eventually start to increase. Okay, and so that's more or less presented here, right? So as lambda gets bigger and bigger and bigger, we probably fit better and better and better. Okay, and then at a certain point, lambda gets too big, and the fit gets worse. Okay, so now let's talk about the variance. Okay. Okay, so we've been talking in terms of constraining, more or less constrained, based on this lambda value. Okay. Another way that we could think about that is flexibility, right? So when lambda is 0, say, then the model is its most flexible, its least constrained. So this means that at low values of lambda, being less constrained and more flexible, there's a larger possible solution space, and so there's going to be greater variance. As lambda gets bigger, then we are constraining the model more and more. We are reducing the solution space, and so variance should decrease. And so the answer should be that the variance steadily decreases as lambda gets bigger. Okay. Well, now how about for bias? Well, let's go back to the image here, and that's what is presented in the image. So as lambda gets bigger and bigger and bigger, the variance gets smaller and smaller and smaller. Okay, because we're constraining the model more and more and more. Okay, so what about bias? Okay. As lambda gets bigger and we're constraining the model more and more and more, another way we could say that is that we are imposing more and more bias. Okay, so as lambda gets big, bias should steadily increase. Okay, and again we see that here in the image, right? So lambda is getting bigger and bigger and bigger, and it's always getting bias is also always getting larger. Okay, might asymptote at certain points, but it's always getting bigger. It's never getting smaller. Okay, finally we have irreducible error. I don't think there's much to be said about this. So again, irreducible error is the error that is always there. It's some baseline level, kind of based on the ugliness of the data or something like that. So for irreducible error, it should remain constant. Okay, we'll call that good.